Today we'll discuss the Taylor and Mclaurin series. In order to find the Taylor series of a function, one needs to be able to calculate all the derivatives of that function on some interval containing a number a. The number a will be given to you in the problem. So the Taylor series generated by a function f at some number x equal to a is given by this formula. This formula needs to be memorized for the final exam. It's a very important result. It will not be provided for you. You must memorize this formula. This notation means the kth derivative of f. When k is 0, we have the 0th derivative. And by definition, the 0th derivative is the original function. Think about it as taking no derivatives. When k is 1, we're talking about the first derivative. When k is 2, the second derivative, etc. In the denominator here, you have k factorial. This summation starts at k equals 0. By mathematical convention, 0 factorial is 1. And when we plug 0 in here, we get x minus a to the 0. And we will assume that x minus a to the 0 is 1. So when I plug in k equals 0 into this formula, all I get is f of a. When I plug in 1 into this formula, I get the first derivative, or f prime, evaluated at a, divided by 1 factorial, hence I have nothing in the denominator, times x minus a to the 1. So I get x minus a as the next term. When k is 2, I have the second derivative, or f double prime, evaluated at a, divided by 2 factorial, which is 2 times 1, times the quantity x minus a squared. When the k is 3, which would be the next term here, I'll have the third derivative evaluated at a, divided by 6. 6 is 3 factorial, times x minus a cubed, and so forth forever, since this is a series or an infinite summation. A Mclaurin series is simply a Taylor series where the a is 0. So I'm replacing a equals 0 throughout the formula, and this is what I get. Notice it simplifies quite a lot. So a Mclaurin series is a special case of the Taylor series. So every Mclaurin series is a Taylor series, but not all Taylor series are Mclaurin series. In today's presentation, we only did one example. We did the example of finding the Taylor series of f of x equal to 1 over x at a equals 2. Originally asked the question, when does the series converge to f of x? This question is going to require a little bit more mathematics and a little bit more theory to figure out when it converges to f of x. So instead, let's simply answer the question, where does the series converge? So for what x values will our power series converge? And that's an important thing to notice here. Both the Taylor series and the Mclaurin series are power series. So in order to figure out the Taylor series of f of x equal to 1 over x at a equals 2, I need to calculate a bunch of derivatives. Every term in the Taylor series requires the next derivative. So I simply find the 0th derivative of the function, which is just f of x. But I'm going to go ahead and write it as x to the negative 1 because I need it to be in a form that's nice to differentiate. And I continue taking derivatives. So to get the first derivative, I simply use the power rule. Then I use the power rule again and simplify to get the second derivative. Then I use the power rule again to get the third derivative, and the power rule again to get the fourth derivative. So going down this first column, I'm simply getting the next entry by taking consecutive derivatives. The second column, I'm simply figuring out what these derivatives are at a equals 2. So I'm plugging 2 in everywhere there's an x. A piece of advice, don't oversimplify here. Simple things like getting rid of negative exponents is okay. But the best way of being able to figure out the pattern that's going to be happening here is to not oversimplify. So I simply plugged in 2 everywhere there was an x into the first column to get the entries in my second column. And I simplified only slightly. I left everything as powers of 2, and that's going to be helpful, because the next thing I need to do is to find a formula in terms of k that gives me these numbers. So I need to figure out a formula for f to the kth derivative, evaluated at 2. The first thing you should notice about the sequence that we have in the second column is that it's alternating. That tells me I'm going to have a negative 1 to the k or a negative 1 to the k plus 1 in the formula. The second thing you should notice is that there are fractions. So I'm going to have a fraction in my formula, something divided by something else. So let's find the formula for the top and the bottom separately. If I notice the numbers on the top, they're following a nice pattern. They're simply k factorial. And the numbers on the bottom are powers of 2, but the powers of 2 is one more than the derivative that we're looking at. And the first one in the denominator have 2 to the 1, which is 1 more than 0. In f1 of 2, I have a 2 to the 2 in the bottom. That 2 in the numerator exponent is 1 more than the first derivative, or 1 more than 1. Likewise, for f to the 2 of 2, or the second derivative of f evaluated at 2, I have a 2 to the 3 in the denominator. So I have a 3 in the exponent, which is 1 more than 2. The same thing happens for the third derivative and the fourth derivative. So it looks like the denominator is 2 to the k plus 1. So the formula I get is negative 1 to the k times k factorial divided by 2 to the k plus 1. The process of finding this formula is just like finding the formula for a sequence like we had at the beginning of chapter 10, except now we're looking at some derivative evaluations and we're getting a sequence built from those derivative evaluations, but the process of discovering this is exactly the same. You look for patterns and then you try to find a formula. Once you have this formula, you should check that it works for each k that you've worked out. So if I plug in k equals 0, ensure that I get f to the 0 of 2. When I plug in k equals 1, make sure I get f to the 1 of 2. And likewise, when I plug in 2, 3, and 4, the same results follow. So now to find the Taylor series at a equals 2, I simply go to the Taylor series formula and plug in the formula for the kth derivative of f evaluated at 2. And then I simplify. After some simplification, I get this series, the series from k equals 0 to infinity, negative 1 to the k, 1 over 2 to the k, times x minus 2, all to the k. This is my first Taylor series that we found. To figure out where this converges or diverges, you simply use the power series method from the last section. We'll run the Rooter ratio test on this to find a temporary interval of convergence, then test the endpoints and see what happens there, and summarize our findings. So to figure out the interval of convergence, we approach this as any power series. Running the ratio test on this series, I find a temporary interval of convergence of 0 to 4. And then testing the endpoints, I'll see that both endpoints diverge due to the nth term test. You need to check that. That does require some work. And if we summarize all this, we get the following. The series converges absolutely on the interval 0 to 4. The series converges on the interval 0 to 4. The series conditionally converges nowhere because the interval of convergence is the same as the interval of absolute convergence. And the radius of convergence is just half the length of the interval divided by 2. In this case, 4 divided by 2, which is 2. Some people say for this kind of a problem that we're looking for the power series of 1 over x centered at a equals 2. And the reason is because this a number will always be the exact center of your interval of absolute convergence. Notice 2 is exactly in the middle of 0 and 4. I hope this helps you with the Taylor and Mclaurin series getting started. I hope everybody stays safe and healthy. Have a great day, everyone.